Hello everybody and welcome to my poster presentation about Higenamine quantification and investigation into structural characteristics of its metabolites in urine samples. My name is Rubio and I'm part of the research team at the Institute of Biochemistry at the Sports University in Cologne. Higenamine is a non-selective beta-2 agonist naturally occurring in different plants such as Nandina domestica or Annona squamosa, for example. In agreement with regulations existing for other beta-2 agonists, the use of Higenamine in sports is prohibited at all times. And according to WADA guidelines, a reported level of 10 nanogram per milliliter applies for the detection of salmeterol and Higenamine, which means 50% of the minimum required performance level for the beta-2 agonists. But in our case, the reporting limit refers only to the determination of the free compound. The herein pilot project was developed in three main steps. First one, the description and fully validation of a quantitative method for free Higenamine in urine, which will enable us, in further steps from this project, to investigate whether the ingestion of tropical fruit plants of the Annona family can lead to Higenamine adverse analytical findings. In a second step, the estimation of the specific contribution of Higenamine metabolites was performed. This contribution has been previously tested. However, in this case, enzymatic hydrolysis was performed in order to estimate the specific contribution of both conjugates groups. And finally, the investigation of metabolites' structural characteristics was also conducted. Regarding the method validation, it was conducted following direct injection approach, and isoxaprine 5 was used as internal standard. The measurements were performed by means of liquid chromatography coupled to tandem mass spectrometry as follows, and the hydrolysis experiments were performed using 20 microliters of beta-glucuronidase from E. coli and 10 microliters of aryl sulfatase from Pseudomonas aeruginosa. The samples were analyzed according to the method already mentioned. And finally, for structural elucidation, solid phase extraction was performed, and then the here obtained samples were fractionated on an Agilent HPLC system coupled to a fraction collector, and then the subsequent LC-MS-MS analysis of these fractions was performed according to the same method again. Here we can see the table in the results from the validation of our method. So the limit of identification, it was 1 nanogram per milliliter, which means 10% of the minimum reported level for Higenamine. We had ion suppression from 42 to 68%. We had an acceptable linearity. We had precision and accuracy below 20%. For the reliability, we had a 100% detection rate. We didn't have carryover, and the stability was assessed by measuring 10 samples from 10 nanograms per milliliter after 24 hours, and again we had 100% detection rate. We have here the results of the hydrolysis experiments, and we can observe extracted ion chromatograms of free Higenamine letter A, glucuronide conjugates letter B, and sulfur conjugates letter C. On the left side, we have a sample in which the hydrolysis was not performed yet. We can observe 0 free Higenamine in letter A, and we have product of sulfur conjugates in soft fragmentation in letter A2. We can observe the retention times match the retention times from the sulfur conjugates in letter C in the same sample. On the right side, we have the product of the hydrolysis using the different enzymes. So in the upper side, we have the free Higenamine obtained by using beta-glucuronidase, and then below we have the free Higenamine obtained using aryl sulfatase. So we can have an idea already which metabolite is the major contributor. Here we have the results of the investigation into structural characteristics of the metabolites. On the left side, extracted ion chromatograms of sulfur conjugates, and on the right side, the ones from the glucuronide conjugates from the different fractions obtained with the HPLC collector. For the sulfur conjugates in fraction 1 and 3, we can observe with the same retention time one sulfur conjugate or maybe two different ones. In order to confirm if they are two different ones, further experiments will follow. And in fraction 6, we can observe with a different retention time another sulfur conjugate. CIT experiments were performed in order to describe potential diagnostic ions for sulfur conjugation sites, and at least for the first sulfur conjugate in fraction 1, the product ions 187 and 244 were detected, which could be related to the two sulfur conjugation sites that are represented in the figure, which could mean that it is a disulfide, and if it's different from the one in fraction 3, they will be two different disulfides. And in fraction 6, we can observe the product ion of 244, just this one, so it could mean that it's a monosulfide. But again, further experiments will follow. On the right side, we can observe at least 3 different glucuronides in fraction 1. For the main one, this potential diagnostic ion for the glucuronoconjugation site was described, the 340, and again in fraction 3 we could observe a potential different one with a different retention time, but again further experiments should follow. To conclude, a major contribution from the sulfur conjugates was observed. The analysis of the collected fractions suggested the presence of at least 2 different sulfur conjugates for higenamine and 3 or more different potential glucuronide conjugates. With the CIT experiments that were performed, we could see the potential presence of disulfur conjugate, or in plural, and 1 potential monosulfur conjugate, but further studies are necessary. And I would like to thank Mafra-Jonik Institute, Federal Ministry of the Interior Community and Building of the Federal Republic of Germany, WADA, and of course my colleagues from Center for Preventive Doping Research, and all of you for your attention.